Hello, everyone, and thank you for joining our presentation. Our project is titled Smart Marketing Predicting Customer Decision in Retail Banking. Before we start it, I'd like to introduce our team. We are a team of 3 data scientists currently pursuing our Master of Applied Data Science at University of San Diego. Our team members are Jun Clemente, Graham Ward, and myself, Michelle Wang. Over the past several weeks, we've worked together to explore how data science and machine learning can help banks improve their marketing strategies. Specifically, how they can better identify customers most likely to subscribe to term deposit products. Today, we'll walk you through our approach, our findings, and how these insights can be applied to create more efficient and impactful marketing campaigns.
Next, let's start with the background and problem statements. The Portuguese bank conducts a large-scale phone-based marketing campaigns to promote term deposits products. These deposits are critical. It helps insurance bank financial stability, in the meantime providing customer with a safe investment option. However, the current approach is broad and untargeted. As we can see here, historical data shows only 12% of customers actually subscribe. This low conversion rate means most costs do not generate value, leading to a higher operational cost and a less efficient use of resources. On top of that, there is no predicting targeting in place. The bank cannot reliably identify high potential customers before making contact. Together, these issues highlight the need for smarter, data-driven approach to campaign targeting. Next slide, who will subscribe? These questions lead us to the key business questions driving our project. First, can we predict which customers are most likely to subscribe to a term deposit? Second, what personal interaction and microeconomic factor drive customer decisions? And third, how can we integrate these predictions into banks' campaign strategy to maximize return on investment? Answering these questions forms the foundation of our goal to build predictive models that identify customers most likely to subscribe a term deposit, enabling the bank to focus on the right customer, improving marketing efficiency, and ultimately increase conversion rates. Next, let's take a close look at the data and we work with and how we explored it before moving to pre-processing and modeling. The data we are using the bank marketing dataset from the University of California, Irvine machine learning repository. It contains 41,000 customer records with 21 variables. With the 21 features covering a mix of demographic details, financial indicators, contact history, and microeconomic data. Our target variable, label Y, tells us whether a customer subscribes a term deposit with possible value yes or no. The key challenge here is that the data is imbalanced. Only about 12% of customers said yes, while the 88% said no. This imbalance is a key consideration in our modeling approach, and it impacts both evaluation metrics and the modeling section, and we will address that in later section.
Next, before we doing any modeling, we performed an extensive explanatory data analysis to understand dataset structure, identify potential issues, and uncover initial patterns related to the target variable. Our EDA process involves several key steps. First, we review the data structure, confirm the variable types, and examine the distributions for both numerical and categorical features. We also addressed missing values, which all know entry is categorical variable. We treated it as a separate category rather than imputed it. Next, we performed univariable and bivariable analysis, exploring relationship between individual features and target variable. This including using histogram, frequency plot, correlation heat map for continuity features, and the chi-square test for categorical features. We will address that one in later. Finally, we identified multicollinearity among certain microeconomic indicators and variables for removal and transformation. These EDA findings directly guide our pre-processing steps, helping us decide which variable to drop and how to encode categorical variables and which features required scaling, ultimately ensure a cleaner, more informative dataset for modeling. Next, let's take a look how we approach these pre-processing steps. I'll now hand it over to my teammate Jun to talk about this part.
Thank you, Michelle. Now, moving on to our pre-processing strategy. We began by cleaning and simplifying the dataset based on insights from our EDA. One important step was addressing multicollinearity, where two or more features are highly correlated. Keeping these together can lead to overfitting and unstable models. We found that emp.var.rate was strongly correlated with Euribor 3M, nr.employed, and cons.price.idx. To reduce redundancy, we kept emp.var.rate and removed the other three from the final dataset. Next, we examined the numerical features for outliers using the interquartile range method. Variables like age, duration, campaign, P days, and previous showed extreme values. Upon further review, the age values were valid and kept as is. However, the variable P days and the variable previous were highly similar. We decided to drop previous and convert P days into a binary variable to simply indicate whether a client had been contacted before. For pre-processing of the categorical variables, we ran chi-squared tests to see which features were statistically significant in predicting the target variable. Features like housing and loan had p-values greater than 0.05, meaning their relationship with the target was not statistically significant. These variables were removed from the dataset. The rest were kept for further analysis. We also used Kramer's V to measure the strength of association between categorical features and the target variable. The strongest predictors were P outcome and month, followed by job and contact. This analysis helped us see which variables were likely to be the most useful for our models. Lower scoring variables were kept in case they could still contribute in combination with other features. Before modeling, we encoded the target variable as 0 for no and 1 for yes. To preserve the original class distribution, we used a stratified train test split, with 80% for training and 20% for testing. The EDA revealed a clear imbalance in the target variable, with far fewer clients subscribing to a term deposit compared to those who did not. To address this, we applied synthetic minority oversampling technique, otherwise referred to as SMOTE, to oversample the minority class in the training set, helping our models learn from both classes more effectively.
In order to evaluate the best approach for predicting customer term deposit subscriptions, our team selected 8 diverse machine learning models, which span linear, nonlinear, and ensemble model types. Our lineup included the perceptron, logistic regression, k-nearest neighbors, support vector machine, neural network, XGBoost, AdaBoost, and random forest models. A unified pipeline for each model was developed, which handled all pre-processing, feature encoding and scaling, and smote oversampling in a consistent and reproducible way. Then, each model was trained and evaluated via five-fold cross-validation on the training set to estimate generalization performance. Then, finally, we tested the trained models on a separate holdout set using 5 metrics: accuracy, precision, recall, F1 score, and the ROC-AUC score to assess the performance of each model. Across the board, all models generalized well, with no signs of overfitting when evaluating performance metrics between the training and the testing sets. The XGBoost model emerged as the top performer with the highest accuracy of 91.6, the highest precision of 63.1%, and the best ROC-AUC score of 94.9%. This means it was most reliable at distinguishing between customers who would and would not subscribe to the bank marketing team's term deposit campaign. The second highest performing model was the Random Forest, which achieved the highest F1 score, showing a strong balance between precision and recall, while also achieving the second highest accuracy of 91.6% and a ROC-AUC score of 94.3%. However, if the priority is to maximize recall, which would catch as many true subscribers as possible, then logistic regression would be the top choice, which had a recall rate of 89.9%. However, overall best performance in terms of predictive capability was the XGBoost model, was clearly the strongest candidate. Based on our results from the previous slide, we recommend implementing the XGBoost model for the bank's marketing campaigns in order to efficiently target potential subscribers for term deposit accounts. We also suggest periodically retraining the model in order to prevent performance degradation due to drift or changes in customer behavior and market conditions, which could affect the target feature. As a follow-up step, we should apply the model to the bank's own internal data set to confirm that the XGBoost model remains the best choice in a real-world setting. And finally, expanding this data set with additional features such as transaction histories or account balances, overdue notices, and other behavioral indicators could further improve the predictive accuracy and campaign success rates moving forward in the future. Thank you very much for your time.